That's a very, very good. So it should be recording. Yep. Okay, and I go to the share screen. And we go to that. So big question, can you see the screen? Does it all work all right? Thank you, Reynolds. That's great. Oh, my connection is very slow today. That's funny. It's really a little bit strange. Yes, it is. Where does the word pH come from? Where does this P come from? I mean, the H is probably, so the H state, the letter H, that is probably self-explanatory. That's from the hydrogen ions. And the P, there are different versions actually. The way, what I have learned is it does not necessarily mean the word power of H. It means the weight of H, which in Latin would be pondus. Pondus means the weight, where also the word pound comes from. Pound, what you pay with, is nothing but a weight in a way. So pH probably means the weight of the proton concentration. So there are different versions, either power or weight. I think we've got people here unmuted, but that's not a big problem because we haven't started yet. But please make sure that you record your attendance on Moodle, and Bernardo has kindly provided the link. Thank you very much again. That's excellent. Yeah, I've also heard the version of potential. I don't think anyone is absolutely clear what this P means, but we are going into that a little bit more today, because there is not just a pH or a POH. There are other P's, if you like. Like pKa, exactly. And again, yes, Joshua, you're absolutely right. This P just simply indicates something with a log. Absolutely right. And we will discuss that in a little bit more detail. Because what we're going to do today is the topic of weak acids. Well, I mean, with the logs and the brain, don't hit your brain with logs. That's not a good thing. Yep, yep. Another excellent. So, okay, let's make a start, because we got quite a bit of ground to cover today. And yesterday, in the session yesterday, I gave you sort of a little bit of a brain teaser, and I want to sort that out because I've given you a 1 nanomolar hydrochloric acid, 1 nanomolar HCl, which you can also write as 1 times 10 to the minus 9 molar HCl. And HCl certainly is an acid. There's no doubt about it. And I asked you to calculate the pH of this 1 nanomolar hydrochloric acid. And what did you give me? I told you the pH equals negative log of the proton concentration. And you gave me pH equals 9. Absolutely right. No, I mean, it is right that you gave me that. But there is a problem, isn't it? pH 9, what is this? Is this acid or alkaline or basic? It would be alkaline, absolutely right. And we have an acid and it turns alkaline, so something is not right. It doesn't make sense, the whole thing, does it? Has it to do with partial dissociation? Actually, in this case, absolutely not, because the HCl dissociates totally. So, what could happen? Let's think about it logically. We have 1 nanomolar HCl, right? That means if we have a liter, we have 1 times 10 to the minus 9 mole per liter HCl or protons, which come from the HCl, right? So far, so good. What else do we have in this solution? And I take a different color. I take light blue. What else do we have? We have HCl. What else is there? It's chloride, yes. And what else? Yes, we've got water. We have got water. And what happens with water? Water can dissociate into what? Yes, it is what is called the auto-ionization. It dissociates into H plus and OH minus. Absolutely right. And you are right, it forms hydronium, but I'm just too lazy to write the hydronium. I just leave it like that. What is the concentration of the protons in water? Let's not worry about who is interacting with which. Let's just focus on the concentration of the protons. Ah, yes, it is absolutely right. And what is it? You mean molar, right? So here the concentration of the protons in the water is 1 times 10 to the minus 7 mole per liter. Absolutely right. So we have basically in our solution, we have 1 times 10 to the minus 7 molar. These are the protons from the water. Plus 1 times 10 to the minus 9 molar. These are the protons from the 1 nanomolar hydrochloric acid. Does that make sense? because the concentration of protons in water is always 1 times 10 to the minus 7 in pure water. So our total concentration of protons would be 1.01 times 10 to the minus 7 molar. Put them together, the protons from water, from pure water, and that is the reason why the pH of pure water is 7. So therefore, the pH of pure water is 7, and our proton concentration is 1.01 times 10 to the minus 7 molar. So if we do the pH now, pH equals minus log of 1.01 times 10 to the minus 7, and we are always in molar. That gives us a pH of 80. It has done it already. Let's quickly go over to my calculator. So we do negative log of 1.01 e to the power of 7, 6.996. I write it as 6.996. Is 6.996, is this acidic or basic? Is it lower or higher than 7? Since 6.9666 is smaller than 7.000, this one is acidic. It is still acidic, although not by much. It's very close to neutral, but it's certainly not alkaline, as we said originally. So we have an acid, we put that in water, and thank God the world makes sense again, because we end up with an acidic pH. Very close to neutral, but still on the slightly acidic side. Hallelujah. Praise the Lord. The world is good. Life is good. We have an HCl, we have an acid, and it still stays acidic. The water doesn't act as an acid in this case. It is still the hydrochloric stuff that tips it into the acidic range. No, the water is not acidic. The water should be pH 7. That is this one here. The water is neutral. It's 1 times 10 to the minus 7. That is neutral. But if you just add a little bit of an acid, then it will become acid, but not alkaline. Why does water ionize? It's a very good question. And the answer is it just simply does. Most substances ionize to a certain degree, but the extent to which it ionizes is very, very small. And I'll discuss that in about 5 minutes. And the reason why I gave you this sort of brain teaser is to really make sure that you understand what we are looking for. pH is the negative logarithm of the proton concentration. Lots of people go for the acid concentration here, but we are actually looking at the proton concentration. And if we have a very dilute acid, as we have in this case, because it's just 1 nanomolar, it's very dilute. With a very dilute acid concentration, we must take the protons from the water into account. Because otherwise we end up with total nonsense. Oh, you are absolutely right, Edith. We will discuss how we are dealing with weak acids. But here we are still working with a strong acid. HCl is a very strong acid, right? But we have a very dilute strong acid. Very dilute, let me write this, make this absolutely clear. Very dilute strong acid. Of course, if we even have, say, a 0.1 molar solution of hydrochloric acid, very good. If we have a 0.1 molar hydrochloric acid solution, do we actually need to take the water protons into account? So we have 0.1, let me write this as 1 times 10 to the minus 1 molar, that's from the HCl, plus 1 times 10 to the minus 7 molar, that's from the water. These are our protons. Now, if you add them together, this is the protons from the acid are so much more than the protons from the water that in this case, the water protons, we don't really need to worry about it. Well, we can quickly do that in the calculator. Let's just do that. We have 1 times 10 to the minus 1 plus 1 times 10 to the minus 7. That gives us this for the total proton concentration. And now we calculate the negative log of that. And we get a pH of very, very close to 1. It's a little bit lower than 1, but we would usually not notice that. So the take-home message is, if the acid concentration is lower than, I would say, probably 1 micromolar, take the protons, take water protons into account. That's a very good question. And I can already reveal that you will get a question like this in your exam. You definitely will get a question like that. I promise you. So yes. Okay, so there was another thing where what I did not expand yesterday on, which was, I told you, pH plus pOH. What was that together? Yeah, that's 14. But where does this 14 come from? Why is it not 42, the answer to life, universe, and everything? Or 6.39? Why is it 14? Jack, you're absolutely right. It's the ion product of water. But what the heck is an ion product? Can you eat that? Have a look at water. H dissociates into H plus OH minus, right? So we can actually write this as an equation. We can write this as once this has sort of, once this is happening, we can write this as a constant, and we usually abbreviate it with Kw equals the concentration of the protons, that's the what we have on the right hand side, times the concentration of the hydroxide ions divided by the concentration of the water. This is a constant, and because it describes this dissociation, it is also called a dissociation constant. Dissociation constant. That's the dissociation constant, and the little w here indicates that it's for water. We usually ignore this concentration here because the water is, it doesn't really dissociate. Water is such, the concentration of this H plus is so little that it hardly makes any dent in the what it takes away. So we see this also as a constant, and we usually ignore that. So what we usually write then is Kw equals H plus times OH minus, right? Now, tell me, what is the proton concentration in water? And we had this already today. What's the proton concentration in water? Yep. Ah, fantastic. Thank you. You put the M. 1 times 10 to the minus 7 molar. What's the hydroxide concentration? Yes, absolutely right. It's also 1 times 10 to the minus 7 molar. Because for each proton that we get, we also get 1 OH minus. So what do we get if we multiply 1 times 10 to the minus 7 times 1 times 10 to the minus 7. One times 10 to the minus 14. What's the unit? In this case, apples, exactly. Well, the way I've written it, it would be molar squared, but if we carry on with the unit for water with molar, it would be probably the one cancels out. But it doesn't matter, because what we usually do is we are not too bothered about this kW. Instead, what we do is we take the negative logarithm of the kW value. We take the negative logarithm of kW, and then the units are not considered anymore. So what is negative log of 1 times 10 to the minus 14? And this actually is called the pKw. Remember we said P, that sort of indicates that we are talking about a negative log. So P stands for negative log. So pH, take the negative log. And that is where this 14 comes from. Isn't that cool? The 14 comes from the ion product of the water, because the water dissociates into protons and hydroxide ions. Now, we talked about strong acids, weak acids, and or strong. What is a strong acid? How do we define a strong acid? And we said, obviously, HCl is a strong acid because it almost completely dissociates into the protons and the chlorides. So that is the definition of a strong acid. So let's have a look. Let's write this in general terms. Let's say we have HA, and that should be our acid. Okay? And this acid dissociates into H plus A minus. A minus here, that's our base. Is it a conjugate acid-base pair, HA and A minus? Is it conjugate? Yes, it is, because it's the same compound and only one proton difference. So that's the definition of a conjugate acid. So what we can do for this is we can do exactly the same as we've done for our water. We can write a constant, an equilibrium constant, where we have H plus times A minus divided by HA. And we probably need to say that this happens all the time once everything has been sort of established. So we write this as sometimes you see it with an EQ at the end here. This means We wait a little bit, and then the acid forms this equilibrium. And what an equilibrium is, we will discuss in more detail in the shortly before Christmas when we talk about kinetics and thermodynamics. But at the moment, this is at the equilibrium. And Ka is the dissociation constant. Dissociation constant of the acid. Okay? I hope it's not too stressful. So, if we have a very strong acid, like HCl, what happens? Let's say we start with, let's say, 0.1 mole per liter. That's this one here. So, at the start, let's have a look. We have basically three things possible. We have HCl at the start, and I indicate that here with start, equals 0.1 molar. Proton concentration right at the start is 0, because we are right at the start. There a picosecond, so that nothing has happened. And of course, the chloride ions at the start is also 0. Yeah, does that make sense? When we have a strong acid, we look at the start here. When we've waited until we've got the equilibrium, let's look at the proton concentration. Do this list. Now, almost all of the HCl has been turned into protons. So at the equilibrium, you would have close to 0.1 molar proton concentration. And the same holds true for the chloride. It's also 0.1. How much of the HCl have we got left when we have the reaction HCl to H plus Cl minus? How much of the HCl is left? Pretty much almost close to 0. Yeah, we totally got that. Now let's put that into our Ka. We said Ka equals our H plus Cl minus, and that's all at equilibrium, divided by HCl at equilibrium. Okay, so we said we have here 0.1 molar, this one, that's this one, times 0.1 molar, divided by this one. and that is close to 0 molar. And the reason why our proton concentration is 0.1 is because the HCl has almost totally dissociated. We started with 0.1, and all of the 0.1 changed into proton and the chloride. A Ka at the start doesn't make any sense whatsoever, because Ka is an equilibrium constant and it has to be done at the equilibrium. So what do we get if we calculate if we multiply something and divide it by something very, very small? What do we get? Ka in this case, is it very small or very large? We divide something by something very, very, very small. So Ka would be very large. Absolutely right. We get something really large, huge. Now, what happens if we do pKa? Well, we just simply say pKa is negative log Ka. What do we get if Ka is very large? Ka, pKa is minus log of something very large. What do we get for pKa if we take negative log of very large? Very small. Absolutely right. So pKa in this case, pKa is very small. If it is exactly 0, you can't calculate it anyway. But if it is just a little bit above 0, that means not every molecule has been dissociated, then you still get a very, very small pKa. So this actually is sort of a definition of a strong acid. Strong acid means very small Ka. Let me highlight that. I know that it is like the green color. So this is what we got. Strong acid means a very small pKa. Does that make sense? Now, what about a weak acid? What about a weak acid? Let's go again for our HA example. That is a general example where HA is the acid, H plus and A minus. So this is the acid here, and this is the base. And again, we can do our sort of what we've done for the HCl. We can say we have start. At the start, let's do it with 0.1 again. 0.1 molar acid. So start. We have HA equals 0.1 molar, H plus at the start and the A minus at the start are both 0 molar, because we are right at the start. At the equilibrium, what is our proton concentration? A minus equilibrium. What would be our proton concentration? Well, it would be, we don't really know. Let's call it X. Okay, let's call it X. We don't know. We don't know how much this acid actually dissociated. But what we do know is that the A minus is the same number, because for each proton we get for each proton that we produce, we get the same number of A minus. So we also get an X here, right? How much of the HA do we have at the equilibrium? Do we still have 0? Is it very small? It's a good answer, but it's not the right one. Var is right, absolutely. We have what we started with, our start concentration, minus what we have lost in this process, minus X. Absolutely right. I like that. Yeah. Now, if the acid, and somebody is not muted with all this excitement, if the acid is very, very weak and hardly dissociate, then our X is very small. Stay with the X's for a moment. I will change it. Don't worry. So what we can do is we can write this here, this part here. We can write this again as Ka equals, okay, so H plus equilibrium times A minus equilibrium divided by HA equilibrium. And now let's plug in the numbers. We said we don't know X. Don't know this one here. We'll just call that X. We don't know this one here, but that's also X. Divided by HA start minus X. And then HA start, that was our 0.1. So that's our Ka. So we can write this as Ka equals X squared divided by HA start minus X. Okay? Makes sense? Now, we said HA start, if it is a weak acid, then X is very small. x is small, because it doesn't dissociate. It does not dissociate really. And HA start minus x is pretty close, and I symbolize that with these wavy lines, is pretty close to HA start. Because if x is small, take away something very small from something, it's still something similar. Can other people see the screen? Or is it me? So people can see. Okay. Edith, you might log out or you might end the call and join again. It looks like it's at your end, the issue. So what we can do actually is we can write Ka equals x squared divided by HA start. Because we said this is pretty similar to HA start. And of course, the whole thing is a quadratic equation, isn't it? So let's try to find out what is x. So what would we do? We would write this as x squared equals Ka times HA, and that's the HA start. We will do an example calculation for that, but not at that point, because I'll give you the equation in a minute for that. So x squared equals Ka times HA start. Okay, I will do that. So what can we do? Just for fun, let's take both sides of the equation log 10. We know how we deal with something like that. This would give us 2 log x. Yeah, that's the rules of logarithm. Logarithms equals log Ka times HA start. So I've taken both sides logarithm. Okay. I can write this here also as log Ka plus log HA start. Again, rules of logarithm. Now, what I do now is I take both sides, multiply them by -1. So we've got 2 negative log x Don't worry, go back to that. We will come out at a solution in 35 seconds. Equals negative log Ka minus plus minus log HA. And that's the start. I just multiplied this -1 into here, and into here, and then into here. So let's remind ourselves, what was x? X was nothing else but our proton concentration. So x is the proton concentration at the equilibrium. So what is minus log of the proton concentration? What is this? I just multiplied both sides by -1 because I just wanted to do that. I felt like it. Yes, this is the pH. So we've got 2 times pH equals, what is minus log Ka? Yes, it's pKa. So we have, and plus, minus, we can't do anything with that, log of the acid concentration at the start. We don't need to worry about how much has been dissociated. So what I now do is, put in brackets, and I divide by 2, because I don't want 2 pH, I want just pH. So I get pH equals 1/2 of pKa minus log of the acid concentration at the start. Does that make sense? And this, ladies and gentlemen, this is the equation for the pH of a weak acid. Absolutely no. You do not remember how you get to it, but you need to be able to use this equation, and you need to remember what this equation is, right? Don't need to remember how you get it, but you need to remember the equation. And we have kept it really, really general. So I did not specify what HA is. We just need to probably say a little bit when we should use that. And we said for a strong acid, the pKa will be very, very small. Of course, for a weak acid, pKa will be large. But what is large? My sort of guide or rule of thumb is pKa larger than, say, 0. If a pKa is larger than 0, it's a weak acid. Or very often what you will find is that for strong acids, no pKa will be given. So if there's no pKa given, no pKa, strong acid, and you would use just simply the equation minus log of the proton concentration. Bear in mind, this could be the acid concentration plus the water protons. Sometimes we just simply ignore the water protons. If pKa is given, and pKa is larger than 0, then pH equals 1/2 of pKa minus log of the acid concentration. Strictly speaking, we need to take the water protons into account, but for the time being, we just leave it like that. So these are the rules. And again, let me highlight this. When we are dealing with acids and bases. So there are lots and lots of practice questions on the website of the practice. Sorry, I should practice. Let me write this. Practice calculations, where you can practice these calculations. So, for example, you might have a pKa equals 4.0. Your acid concentration is 0.1 molar, and the pH of that would be pH equals 1/2 of 4 minus log of 0.1. So it is 4 minus log 0.1 is -1. Half pH equals 4 minus -1, that gives 5. The pH, therefore, would be 0.5. Simples. Any questions? Thank you very much, Müller. So please practice these calculations because they will come up in exams. And we will need something like that for tomorrow's session when we are going to deal with buffers. So thank you very much, and I hope you have a wonderful rest of the day and you recover from all the pH, pKa's and logs, and your brain stops hurting. Thank you very much for watching, and I shall see you tomorrow.